everybody. In this video, we're going to continue our dive into radical functions through the enVision Algebra 2 math book. We're going to look at example 3 from lesson 5.3, and we're looking at rewriting radical functions to identify transformations. So again, to refresh your memory, we have f of, let me change that color really fast. I was using yellow, I kind of like the yellow. F of x is equal to a and root x minus h plus k. That's a k, not like a 1c. There we go. All right, so if I'm given a function, let's say I'm given the function g of x, that should be a g of x, not h of x. Our original function is this guy. So let's say I'm given the function g of x equals the square root of 9x. Well, here's a case where we don't actually have something being multiplied to the x. We don't have a b in here. We don't have a scaling. We don't have a horizontal scale. We could say this is a horizontal scale, but we could also kind of break this apart and clean it up so to fit the format that we're given. So in this case, remember, if you have a times b, I can rewrite this as the square root of a times the square root of b. And I could do this with any roots, not just square roots. So that's what I'm going to do here. I'm going to take the square root of 9 and multiply that by the square root of x. Okay, now I'm just going to simplify. The square root of 9 is 3 times the square root of x. And now we see we have the a scale factor. So a is equal to 3. We don't have an h, nor do we have a k. So the graph is stretched. So the graph is stretched because 3 is greater than 1. So the graph is stretched. Vertically by a factor of 3. Now, what does that mean? What are we looking at here? So here's my graph. And if I were to take my straight lines, which are not going to be very straight this time around, okay, that's horribly straight. Let me go back and make the straight lines. I thought I could do it. I thought I could get by with that straight line, and I obviously could not. That was pretty sad and pathetic of a line. Poor line. If I need a crooked line, that was a perfect crooked line. Okay, so the parent function was something of this sort. 1, 2, 3, 4, 1, 2, 4, 5, 6, 7, 8, 9, 1, 2, 3. Because remember, the square root of 9 is 3. 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4. So I'm looking at perfect squares, and I'm drawing them out that way. The domain is x greater than 0. The range is y greater than 0. But the child function, the g of x, we're scaling up by a factor of 3. So each one of these output points, we're going to multiply 3 to. So 0 times 3, well, that's still 0. 1 times 3 is 3. 1, 2, 3. 2 times 3 is 6, so 2, 3, 4, 5, 6. This is 3 times 3 is 9, so 3, 4, 5, 6, 7, 8, 9. And 4 times 3 is 12, so that's 9, 10, 11, 12. So my new function, it's like somebody came in and just grabbed the top of this graph and pulled it up. We're being pulled up, we're being stretched. And so this is what the new graph would look like. This was what the transformed graph would look like for this example. All right. Now let's get into something a little bit more complex. Let's get into something that is not exactly a perfect square root. I mean, it's going to be a perfect square root. They choose a perfect square root for an example, but something that's not going to be as obvious as the one we just went through. So let's look at h of x is equal to the square root of 4x plus 16 plus 7. Again, in all the transformations for radicals, we don't have this scaling factor. We don't have the horizontal scaling factor. So I have to take this out. I have to take this guy and basically make him a greatest common factor and pull it out. And that's what I'm going to do. I'm going to divide each of these terms by 4. And that will leave us with 4. 4 divided by 4 is 1, so that's just going to be x, plus 16 divided by 4 is 4. So we were very nice to have this as a whole number. This can actually end up to be a fraction. And this can very much end up to be a decimal. Okay, again, taking into account that a times b, I could separate as a times the nth root of b. I'm going to use that here. So we have the square root of 4 times the square root of x plus 4 plus 7. Four is a perfect square, so when I take the square root of it, I get the value of 2 times, I guess I don't have to put the times, x plus 4 plus 7. So now what I'm looking at is, A, we have a scaling factor, so we have a vertical stretch by a factor of 2. We have a horizontal shift left 4 units, and we have a vertical shift up 7 units. Okay, so let's look at my graph. I'm going to have to move him, or I could just move this guy's out of the way. No, I'll just move the graph. Move him right there. All right, so we're going to go back 4 units. So as opposed to that last one that I did, when I did not go back all the units I was supposed to, I'm going to move this back a little bit. But we do go up pretty high, so I'm going to bring this down here. Draw my line here. Doop-a-doo. Flip this around. And I'm going to make sure there's 4 units. 1, 2, 3, 4, 5. Or go here. So parent function again, 0, 0, 1, 1, 4, 2, 9, 1, 2, 3, 4, 3, 1, 2, 3, and then 16, 1, 2, 3, 4, 4, 1, 2, 3, 4. Parent function there. Horizontal shifts, I told you I do horizontal shifts first. It's just my preference to go back 4 units to do something that's happening inside the radical and then take everything that's happening outside the radical. So I'm going to go back 4, 1, 2, 3, 1, 2, 3, 4. Go back 4 with each dot, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, now the blue dots are the dots I'm going to follow next. I'm going to do my vertical stretch by a factor of 2. I'm going to make this green. So 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. 1, 2. What is this? 3. 3 times 2 is 6. 1, 2, 3, 4. So 2 plus 4 is 6. And this is 4 times 2 is 8. So I go 1, 2, 3, 4. Did I just say 2 times 2 is 6? 2 times 2 is 4. I was thinking of the last example where we were looking at 3. So, oh no, 3 times 2 is 6. Yeah, 1. Yeah, that's right. Never mind. 1, 2, 3, 4. I don't know what I did there. My brain malfunctioned for a split moment. It's a little bit longer than a split moment. Okay, so now I'm just going to take each of these green dots and I'm going to move them up 7 units. So 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And now this is my new graph. And then this pink one was my original. This is h of x. And then this one, I'm just going to use the same color, is f of x, or your parent graph. All right, so the graph of h of x is a vertical stretch of the parent function by the factor of 2. And then it's followed by the translation up 4 units, and then the translation 7 units. Like I said, I do my translation or my horizontals first, and then my verticals. Sevis does the stretching and then the translation. Either way, it does work out as long as you keep track of your points. All right, so that is for the rewriting radical functions so that we could get the proper notation for transformations that they give us. I will see you guys in the next video.